Bismillahirrahmanirrahim. Welcome to the third part of lecture 1. So this part is about the design cycle or flow. So what this means? This means that what are the steps involved in a chip design. Okay, if you remember, I have told you that we use softwares to design all the transistors on the chip because it is impossible for humans to deal with such complexity. So here in the slides you see these steps that are followed for a chip design. So usually the first step is you start with system requirements. For example, system requirements may be that your circuit should work for a maximum frequency equal to or less than 100 megahertz. So this is a design requirement, and for this requirement you have to design a chip, a circuit on a chip. Okay, so normally this is just one requirement. There can be other requirements. For example, the power consumption should be less than, for example, 10 milliwatt. Okay, so usually these requirements comes from the user. Then the next step number 2 is architectural definition and logic design. So in this step you start with some form of capturing the design. For example, I told you in the last part you can capture your design in C or C++. Okay, so for example, this may be an FIR filter. First, I think you have taken digital signal processing course. So maybe you have a code for FIR filter, and you want to design a chip for implementing this FIR filter. So your starting point may be C or C++. Then there are software tools which are called high level synthesis or HLS. The HLS tools takes your C code and generates gates for you. So this is one way in which you can start to develop your design and map it onto gates. Then there is another way which is called Verilog. This is a language. It's language which we call HDL, hardware description language, HDL. So we describe our design in HDL, and then from HDL there are software tools, okay, which are called, for example, synthesizers. Synthesizer is one of those tools. This can give you gates. Okay, so essentially you start from either from a higher level language like C or C++, and you go to the gates, or you start from Verilog HDL, which is another language, hopefully you will study, and you go to the gates. Now the gates is what is called logic design. So the second step is logic design. Now the third step is design verification. What we mean by design is verification is that we have a circuit just like we had circuits in DLD. So DLD circuits, which consist of gates, and those gates we get from step number 2. Remember that the synthesizer, you cannot synthesize large circuits without these softwares. For example, if I ask you to design a circuit, a gate level circuit for 64-bit adder, it's very difficult, because if you remember in DLD you only designed circuits for, I think, 3 variables. Your K-map was 3 variables or 4 variables. So beyond 4 variables you could not design with K-maps. So that's why these synthesizers are very effective, and they are must if you want to design the logic circuit. By logic circuit I mean the circuit which has gates like AND or XOR. You cannot design those circuits without synthesizer. So synthesizer is a piece of software that is required for designing a DLD like circuit. Now the verification step is a sort of check if the circuit designed by the synthesizer is correct or not. Okay, so here there are another set of softwares, set of tools or softwares which automatically verifies your circuits. And how they verify? They verify like this. For example, this is your DLD circuit, DLD like circuit. It applies all the inputs and it generates the outputs, and then it has the verifier has already correct outputs stored somewhere. So what it does, the verifier does, is it just puts a comparator there and checks if the results from your synthesized circuit is equal to your golden circuit or golden result. The golden result are the results which you know they are correct. So for example, if this is a 3-bit input, the synthesizer will apply all 2 power 3 inputs, which are 8. It will apply all the 8 inputs to this circuit and will check the results if the results are correct or not. And if the results are correct, then we go to the 4th step, which is VLSI design and layout. Now by VLSI design mean that we want these gates which we have from the above steps, we want these gates to be made of CMOS transistors. Okay, so we want these gates to be CMOS transistors. So normally, as I told you before, there are several things to consider here. One is device models. This is a sort of library of gates. For example, this may be a library that Intel uses, and this library may have, for example, 4 input AND gate. It may have a 2 input XOR gate, okay, but maybe no 4 input XOR. There may be no 4 input XOR, and if you want to make a 4 input XOR, you have to use multiple XOR gates. So this is the concept of a library. A library is the set of gates that are frequently used by a company, and these gates are what they can easily manufacture. Okay, they can easily manufacture. So for example, the 4 input XOR gate, maybe they cannot easily manufacture, so they decide not to put it in their library. So every semiconductor manufacturer has this kind of library, and this library is what corresponds to the fabs. It is according to the fabs. Fabs are the industries that physically manufacture the chip. So this library is according to the fab's requirements. And so in the fourth step, one thing we do is we map from gates to CMOS transistors, okay, and these or we can say to library gates. But these library gates are not like in this form, they are in transistor forms. So they are like huge chunk of transistors connected in some fashion, okay. So this is called technology mapping. This step is called technology mapping. Tech mapping. So I repeat it again. Tech mapping is mapping from your logic gates which are the result of synthesizer to library gates, and library gates are the gates that you can manufacture, okay. So one are logic gates, they do not have anything to do with manufacturability, and the other are library gates, which is what you can manufacture. So this technology mapping is about this. This is about mapping logic gates to library gates. Then the next step is this layout. So this layout is about the creation or generation of mask. So in the last part I told you that chips are manufactured by using a mask, and this mask is exposed to light. So we throw light upon this mask, and the reflection and the silicon that is below the mask, this circuit on the mask is transferred to the silicon. So it's something like this. You have here silicon, here you have mask which is generated from layout, and here you have light. So you throw the light, the shadow of or the pattern of it is transferred to silicon, and then we process the silicon, and finally the chip is manufactured. So this is the fourth step, has two parts, which is technology mapping, this one, and layout generation. Okay, these are the two main parts. The fifth step is again verification, design verification. So what is the difference between design verification at step 3 and at step 4? In step 3, your design was logic design. In this step, your design is a physical design. This is a physical design, means that it uses gates from a library, and those gates can be manufactured, and you have the mask. So in this step, the purpose of this step is to verify if the mask is correct, because remember, if the mask is not correct, your silicon will be faulty. So again, this mask is verified, and what can happen to the mask? For example, maybe the mask has a VCC which is shorted with a gate output, and this is what you don't want. But maybe in the process of generating mask, this happened due to some reason. So maybe your gate is, output of your gate is connected to VCC. If the output of your gate is connected to VCC in the mask, this means that the output of the gate will always be high. So this is wrong, because in that case the inputs to the gate will be useless. So this is an example of what is a fault in the mask. So you verify all these kinds of faults that they do not exist. This is called design verification at the fifth stage. And then the sixth step is the mask generation. So it is the output of the above step. And then the seventh step is silicon processing. And silicon processing is something that is done by not by electrical engineers, but by people from chemistry and people from physics and all these areas. So they take the silicon wafer and they process it through machines in a careful environment, in a carefully controlled environment. So they process silicon, and the last step is that the wafer which has the chips. So wafer is like a plate. It's like this kind of plate, and it have multiple chips. Okay, and they are finally cut by machines to get the individual pieces of chips, and then when they are cut, they are put into a package like this. You may have seen ICs. So from here, from the wafers, they are put into this kind of packaging, and after that again they are tested if the ICs created are okay or not. Okay, just to let you know that with each lecture slide I am uploading two kinds of PDFs. One is this one on which I write. This is called annotated PDF, and the other version will be clean. On the clean version you will not see any writing. Okay, so this is for you to consider when you are studying these lectures. Again, let me tell you, if you feel like you can't understand this at the moment, it's okay, because remember, this is the first week and it's all about telling you the whole story. So obviously, in order to learn this, you have to spend the whole semester. So this is just like the overview of all the things that are coming up in this course. So if you can't understand something right now, it's okay. I'm just telling you all the steps, and in the course, each of these steps will be further clarified. Okay, so again, the same diagram. So in another kind of explanation, so the first is functional specification, and by functional specification I mean you specify it in C, C++, or Verilog. So for example, you may want to design a filter, and you can write the filter in C or C++ or Verilog. So here is an example. So this is an example of a adder. So this is a full adder. A full adder has 3 inputs, A, B, C, and it has 2 outputs, sum underscore out and carry underscore out. So this is a kind of, for example, you want this adder chip to be manufactured. You want this adder IC to be manufactured, and you have the variables, input variables, and you have the output variables of this chip. And this is the functional specification. So this is a description. So this is a Boolean. This is a Boolean equation. Okay. Currently, it's not in Verilog, but we can very easily write it in Verilog. Okay. Later in the course, we will see how we can write it in Verilog. But this is the functional specification. You see, sum is A XOR B XOR C. Okay, and carry out is equal to AB or AC or BC. So this is AND gate, and this is OR gate. Okay, and this one is XOR gate. So this circuit come from your DLD course. So this is the circuit or the Boolean equation for 1-bit full adder. We want to manufacture a chip for this adder. Okay, so what are the steps? The first step was this. First step was this functional specification. Okay, and so what we do, this is the Boolean equation. For the Boolean equation, we write Verilog code, for example. So we may say assign sum underscore out is equal to A XOR B XOR C. So this is XOR in Verilog. Don't worry if you don't understand this, but we will learn the Verilog language. So you write it in Verilog, and after you have the Verilog code, you input it to a synthesizer. You take this, you input this, you input this to to a synthesizer. The input is Verilog. The output is logic gates. So DLD9 gates. Okay. Then the next is design specification, which are these two parts, which is this one. This is sometimes called the physical design. These two are sometimes called logic design. So logic design and physical design. So we talked about this in detail, that the physical design is about physical library gates, and it is about the generation of mask. Okay. So you may have certain design specification. For example, the user may want that your propagation delay should be less than 1.2 nanosecond. Propagation delay, sometime we denote it like TPD. So TPD is less than 1.2 nanosecond. What this means, if this is your chip and you apply an input and this is your output, so the total delay from here to here should be 1.2 or less. This is the propagation delay. The next is the next design specification from the user is the rise and fall times of sum and carry out signal should be less than equal to 1.2 nanosecond. So what is the rise and fall time? We will study in detail, but just to introduce you here. So if this is a digital signal, you see, for a signal to go from 0 to 1 in a straight vertical line is impossible. So what actually happens is you have a 0, but the one signal goes like this and the 0 comes like this. So you see, this goes slowly. Okay, so this is called the rise time, and this is called the fall time. So the user wants that the signal should rise in less than 1.2 nanosecond from 0 to 1, and it should fall in less than 1.2 nanosecond from 1 to 0. Another requirement from the user is this one, that the overall chip area should be less than 15 micrometer square. So this is one side, this is the other side. So the total area should be less than 1500 micro square. This is in some micrometer, this is in some micrometer. If you multiply the length and width, it should be less than 1500 micrometer. The other requirement from the user is the power dissipation at 5 volt VDD, and maximum frequency of 20 megahertz should be less than 1 milliwatt. So these are all the design requirements. Whether they can be met or they cannot be met depends on the physical design. Okay, so it depends on the physical design, the library gates, how the library gates are placed, how the layout mask is generated. It depends on the layout mask. Okay, so again, this is the architectural definition of the equation. So we can design the adder also like this. This equation for sum, can be optimized like this one. So this is an optimized equation. Remember that in DLD you used K-map simplification, and K-map gave you a simplified equation. Okay, so the synthesizer can generate, synthesizer have built-in optimizer just like K-map, but for any number of input variables, not just 3 or 4. They have optimizers that can generate optimized equation for 8 or 9 or 10 or 32-bit inputs. So these are very powerful software that can generate these equations. So this is architectural exploration, and if this is an optimized equation, what is the benefit? Use of carry out to realize sum out reduces the circuit complexity and die area. So the synthesizer gave you an optimized equation which has the benefit to reduce circuit complexity and the chip area. It can reduce the chip area because of this equation. So this is that equation, and this is the gate level schematic of a 1-bit full adder. You see here are all the logic gates. We have OR gate, we have AND gate, we have NOR gate, okay, we have NOT gate. So this is the logic diagram of the equation which is generated by the synthesizer. Remember, you just input the Verilog code to the synthesizer. What you done, you wrote the Verilog code, and the synthesizer, what the synthesizer has done, it has generated this whole circuit. This whole circuit is generated by the synthesizer, and it has generated the most optimal, the most efficient circuit. So you can control the behavior of synthesizer. You can tell the synthesizer, okay, I want a circuit that is speedy, that has very high speed. I want the circuit that is energy efficient. Okay, I want the circuit that has smaller area. So somehow the synthesizer can try to give you a circuit which respects your needs. Okay, but sometimes for very complex circuits you have to help the synthesizer. It may not be able to give you the perfect circuit because it is a software, it is not intelligent. It is made to work for certain cases, and if those cases are not what can be applied, then it will fail. So for most of the users, the synthesizer is good enough, but for very advanced user, the advanced user has to help the synthesizer. Okay, now this is the physical, we are entering into the VLSI design. So you see, this is a circuit which has, I don't know how many transistors, we have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So we need 28 transistors for a full adder, and a full adder can add just 1-bit numbers. What if I say I need a 32-bit full adder? Okay, so that is very complex. A 32-bit full adder is very complex, and it is impossible for human to generate the transistor level circuit of a 32-bit full adder. But the magic is that you just tell your synthesizer, okay, that no, the adder, you just modify your adder code, okay, and all the adder inputs, you just say all the adder inputs. So you can write like this statement: assign sum A plus B plus Cn, and you say input 31 down to 0A. So for one bit it was like this: input A. But for 32-bit you add this vector, and just by this small change the synthesizer can understand that you want a 32-bit adder, and it will generate this circuit for you. Okay, then this is the second one. This is, so that step, in the VLSI design, it generates the physical gates. So these are the physical gates. Later in the course we will see maybe this is a NOT gate, okay, maybe this is a NOT gate, maybe this is a AND gate, okay. So later in the course we will see the structures of how we develop AND, NAND and all these kinds of gates. But they are physical gates, and they are what is found in your library. So the next step is this: okay, you have the physical gates and you map it to a layout or mask. You see, this is the mask. It's very colorful image, and on the left you see there are different kinds of legends. So N-well, P-well, N plus, poly, gate oxide, field oxide, metal 1, metal 2, metal 3, contact. So in the later part of the course we will understand about the layouts. We will understand how we go from physical gates to layout. Okay, this is our goal, I think, in the third week or second or third week. So we will understand how this schematic can be translated to this kind of layout or mask. And the final step is design verification. So now you have the mask and everything. You verify it in, for example, PSpice or something, Okay, and you may see, for example, you apply the inputs, and you may note that for C out signal you have this TPLH, which is the pulse low. This is low and this is high. The pulse low to high time, it's almost like, you see, it's almost like 2 nanosecond. So it's like 2 nanosecond. And your user requirement was this. This was the user requirement. User requirement was 1.2 nanosecond. So you see, it is greater. 2 is greater than 1.2 nanosecond. So the spec is not met. Okay. So you have the design, you have the mask, but unfortunately what the user required is not met. Then what you do? You modify, you have to modify the layout. You have to modify the transistor length and width. Later in the course we will understand what is the transistor WL. So these are the physical dimensions of transistors. In order to get 1.2 nanosecond, we have to modify the physical structure of transistor. Okay, we cannot get 1.2 nanosecond. Consider more compact placement of transistors and reduce the interconnect critical paths. So I told you before that if you have this area for your chip, you may decide that a transistor may be placed here, okay, and another transistor may be placed here, and these two transistors may be connected. So for example, they may be connected like this, okay. But this is one option. Maybe if you put one transistor here and one transistor very close to here, maybe they can be very efficiently connected. So here the path is longer, here the path is shorter. So what this means is you have either to do this or either have to do this, okay. And again, all this is inside the layout. The transistor placement is also inside the layout, okay. So I hope that with this third part of the lecture you have seen, and I hope that you have understood to certain extent what is the life cycle of a VLSI design. So starting from the user requirement to the generation of mask, this is the whole life cycle of a VLSI design. I hope that you have understood to certain extent this life cycle, but if not, don't worry, because we will do the same thing in the entire course. The entire course is about this life cycle, okay.